All right. Before we get into the algebra, we're going to do a little visual that relates us back to what we did with polar coordinates. So this idea of a general UV transformation, right now, let's actually see what that would look like with polar. So I'm thinking of U as R and V as theta. And what we found last time was this polar rectangle. So with this what's actually a square in this case on the left side, we'll trace out this shape on the right-hand side, which we call a polar rectangle in XY plane. And the idea is we could take a region that is defined in terms of circles, or some section that looks like circles, and chop it up in these polar subrectangles, because then when we go and do our calculations in polar, it's a much easier region to deal with. And we found we can do that no problem, except that the only way to actually accurately calculate the area of these little polar subrectangles is to take into account that the area is not just going to be dr times d theta, which would just be, think of dr as this little horizontal distance and d theta as this vertical distance. That area of the pink is not just dr d theta, it actually ends up being r times dr d theta, which is why it gets less as we move smaller in r and more as we move larger in r, and it stays the same as we move in theta. And so we can do the same idea. We don't have to necessarily chop in the spiderweb pattern along r and theta. We could chop a totally different way. And so let's actually imagine let's see, we're now trying to integrate over this region here in red, or maybe we've chopped up a larger region into little sub-rectangles that have this red shape. And the idea is if we wanted to integrate this in Cartesian, it's super messy. If I'm shooting my arrow parallel to the y-axis, I'm going to have to do more than one integral to do this, because you can see I enter and exit along different curves. And so rather than doing more than one double integral, and again, remember, this is the base of the mountain. So you have a mountain that's coming out at us. That's your integrand. So we're just saying, how could I chop up this mountain if this was just the base? This looks messy to chop it this way, but it looks way easier if we chop it along lines that are parallel to the sides of the parallelogram. And that's in fact what happens with this particular transformation. And we're going to do this in example 2. So you'll see exactly how we come up with it. But notice that means this red area is now mapped to this blue area. And we can even trace out as we move along a given side. Here's exactly how these x and y points get translated to my u and v points. What that means is it's now much easier to integrate over this region in my UV plane. And you can even see how that changes if I do things like this. Let's see. But one of the problems, let's clear the traces because we need a new. One of the problems with this is that the area in red now, I need to figure out what is that area in terms of u and v and delta u, delta v. And that's where this area expansion and contraction factor comes in. And so we're going to be really interested in calculating how this red area relates to this blue area. We're going to do this analytically by realizing this is a parallelogram, and we can find the area of parallelograms using cross products. So we're about to do that next. But I want to show you an even more interesting one where your region, oops, let's see if I can find the one I was looking for. Oh, here we go. This is the one I wanted. Your region over here doesn't even have to be like on my right side here. It could be something super complicated like this. Maybe I want to integrate over this entire shape. And instead of chopping it up along x and y, because maybe that's too complicated in my integrand for whatever reason, I've decided I can chop it up along these black curves. And those are going to map to, in this case, it maps to these perfect squares in u and v. This is a different transformation. In this case, I'm letting x be u squared minus v squared and y be 2uv. And again, we'll talk about how to come up with these specific transformations in our example. But what I'd like you to see is as I move around, see if it's going to let me, there we go. Okay, so what I need to know is if I take my original region, which has this base in red, and I translate it to a much easier one in blue, I need to know what does my dA become? What's the area of this red region in terms of UV and du dV? And we can see it's going to change depending on both U and V, where I am. And so that's got to be taken into account when I rewrite the integrand. So this area expansion or contraction factor that you see is being calculated up here is what we call the Jacobian. And in our warm-up example, that was just the number 6, which was the factor we were shrinking by. Here you can see the Jacobian is going to depend on U and V. It's no longer just going to be a constant like we had with our warm-up. So let's go and see how we can find this Jacobian in general, which is the expansion or contraction factor that will give me this red area in terms of the coordinates over here.